So in Chapter 3, Part A, we looked at different qualities that we can look at to assess how acidic something is. So now we can use that into action. So we looked at individual examples, but sometimes more than one of the ARIO comes into play here. So if we look at ethanol and propylene, which one is going to bear the load better? Which one is going to be better at holding the negative charge is what you want to ask. So again, you want to compare the bases. So draw the conjugate base. Which is already done here. So we've removed the H from both of these. So we have an O minus and a C minus. You want to compare them in the column. You want to look at the atoms first. So we're going to look at oxygen versus carbon carrying the negative. That battle goes to oxygen. And then resonance-wise, there's no resonance ability for this, but this one can have resonance. And then we look at induction, which is 0. There's no induction here. And then for orbital, this has orbital going for it. So if you were adding up the columns, this would be 1 to 2. So you think this one would be the better at bearing the load. But you don't want to add up the columns. The order of priority goes in order here. So we want to look at atom first. So atom is generally more important than the negative charge. So the oxygen here is going to be better at carrying the negative charge, and we're just going to stop at the atom. So if you look at the pKa's of ethanol, which is this structure here, that one is actually around 16. And the pKa of this hydrogen here on the sp3 carbon is 43. So this will be better at bearing the load for the negative charge because of the oxygen negative, and that has a lower pKa, so that one is more acidic. Okay, so below is the structure of aspirin. Which of the protons indicated is more acidic? So in other words, which one bears the charge better? We want to draw the conjugate base for both of those. So this would be O minus. And then we'll go through atom, resonance, induction, and orbital. So I'm going to call this A. This is B. So we have a column for A and B. If we look at which atom is carrying the negative charge, the oxygen is carrying the negative charge, or B. So this one goes to here. Resonance-wise, they can both have resonance structures. So this is a tie. Induction is a tie because there is none. And then the orbitals, they're both in the same orbitals. So we have a tie here. So based on the atom, this is better at stabilizing a negative charge. So that one is more acidic. And if you know your pKa's of a carboxylic acid, that is around 5. And for this proton next to a carbonyl is around 20. If we need to predict the position of the equilibrium, as in is it more product favored or reactant favored, you have to look at the pKa values. So if you know the pKa values and you've memorized all of them, that is definitely a way to predict the equilibrium. So the side with the higher pKa is favored. But if you forgot the pKa's and you don't know them, then we can use the ARIO. In the reaction below, is it reactant or product favored? So if you know your pKa's, then you are done with this and you can pick it quickly. But if you don't know your pKa's, we can use ARIO, which is the atom, resonance, induction, and orbital. And you want to make sure to compare the bases. First, we have to identify our bases. This is a carboxylic acid, sodium hydroxide. If you can't remember which is which, you can look at the product if it's available, or think of sodium hydroxide that is a base. So this is our base. This is the acid. If we're going backwards, this is the O minus, so this is the conjugate base. And this is the conjugate acid. We're going to compare them using the atom and resonance, and if we need to go further there. Atoms carrying the negative charge. Here we have an O minus versus an O minus, so that is a tie. And then we have resonance. This one does not have resonance. This one has resonance, which means this is better at stabilizing. So this is the side of equilibrium that is favored. So that is how you would do those problems. So again, you're comparing the bases and looking at them to see which is better at stabilizing the negative charge. We look at which side is favored in this example. We want to find our base, and the bases are usually negatively charged. So this is our base, conjugate base, So we're going to look at the atom first. This is N minus versus N minus, so that is a tie. Here, both of them have the ability to draw resonance structures because there's the 3 atoms. This is the sp2, so we could draw a resonance structure here or one here. So they both have resonance structures. I'm just going to draw those down here. So you can draw resonance structures for both, but one thing that you will notice is that the negative charge is on the sulfur versus the oxygen. So we're kind of doing another atom comparison. And in this case, sulfur is better at stabilizing the negative charge because it's larger versus this one. So the equilibrium is going to favor this side. So we don't really have to worry about the inductive because neither has inductive effects, and the orbital is also not relevant here. So that's how you could go about reasoning that out. Which side of the equilibrium is favored here? So you can take a minute, pause, and then try to figure out the problem. So this is the acid, base, conjugate acid, conjugate base. We're comparing the 2 bases, so I'm looking at this one versus this. If I look at atom, I have O minus versus Cl minus. If we look at the atoms here, we have chlorine versus oxygen. Chlorine is better at holding the negative charge versus oxygen, so that one would take the cake here. And if you want to double check with your pKa's, this one is around 5, and the acid here is -5 or something along those lines. So this is going to be the side that is favored in equilibrium. Other things you want to look at is the choice of reagent for the proton transfer. So would water be suitable for protonating the following ion? So what you can do is draw the equilibrium. So we're trying to determine if water is strong enough to protonate to give us this product. And then we're going to compare the stability of the bases. So this is our base. This is our conjugate base. So the atom here is O minus versus O minus, so that is a tie. This has resonance. This does not. So this side is favored. So the reagent only works if equilibrium favors the reagent, so this is not suitable. Another important skill is to be able to choose the right solvent for an acid-base reaction. So you want to choose a solvent that would be able to surround the reactants and facilitate the collisions without self-reacting. Because water can act as an acid or a base, it has a leveling effect on strong acids and bases. So acids that are stronger than H3O+ cannot be used in water, and bases stronger than OH- cannot be used in water. If you were trying to use something with water as a base and you didn't want it to react with water, you want to make sure that it is not going to react with water. So this, in this case, O- can react with water to form the carboxylic acid. So the pKa of this is around 15.7. This is around 5. So this will react with water. So it does react with water, but the equilibrium is favored this way. So you can use water. So if you use water with H2SO4, this side of the equilibrium is favored, so this would not be a good choice. So if you want to use water and it favors the reactant side, then it's okay to use it, but if it favors the product side with water, then that is not a good solvent. Bases stronger than OH- cannot be used in water, so water would not be a good solvent to use for this reaction. This pKa is around 25, but the pKa for this is around 38, so this would favor this side, so we would not want to use water in this situation. So if you had water here, this base would grab that proton first and then become that. All right, we also want to talk about Lewis acids and bases. A Lewis acid accepts and shares a pair of electrons, while a Lewis base donates and shares a pair of electrons. These are usually negative or partially negative. So the water here is partially negative. This is the Lewis acid. It is sharing the hydrogen. This is the Lewis base. And so you have that there. And then if you have the option of a transition metal, or one of these, this is a Lewis acid. It is sharing the electrons with the water. This is a Lewis base. So these electrons are shared right here. These are shared. So identify each of them. The one that is partially negative is the Lewis base. This is the Lewis acid. Lewis acid. Lewis base. Practically speaking, in your textbook they have some of these real-life examples. So this one talks about baking soda and baking powder, and we know that those are needed for baking. It makes the dough or batter fluffy and creates bubbles in your food, which is where the fluffy comes from. A lot of times you will add sodium bicarbonate or baking soda, and what happens in your dough, you have baking soda, which is the bicarbonate, which is acting as a base, can grab a proton from whatever acidic source that you have, maybe it's lemon juice or buttermilk, and that will grab the hydrogen and then leave the A-. Carbonic acid breaks down to CO2 and water. This creates the bubbles in your bread or your baked goods. Sometimes you might add potassium bitartrate, which is in baking powder. That has baking soda also in it. So this is acting as the acid and the base together. So the baking soda is slightly basic and it needs to react with something acidic in order to create the CO2. So the mixture doesn't react until water is added. So you have sodium bicarbonate, and these are two dry things together, but when you add water to it, they go into solution. So this O- can grab a proton from the baking powder to give you the carbonic acid, which will break down into CO2, and then you have this tartrate left over. So the exact ratio of the acid base is important. If you're using something like buttermilk in pancakes, that can act as an acid, or lemon juice can. You don't need to add as much baking powder. If you've ever done any baking and your things taste bitter, it might be because you added too much base, and if something is sour, it's probably because you added too much acid. So you were baking and you were doing organic chemistry, but you didn't know it.